Hello everyone, I'm Dr. Samidhi Navaratna, Senior Lecturer from the Department of Community Medicine. This is the second lecture on Inferential Statistics. I hope by now you are well conversed with what we learned in the previous lecture, that is Inferential Statistics 1. If you have any problem, doubts, you can always contact me and I'll try to do my utmost to help you. Before I start on the lecture proper, I would reiterate some key points we discussed in the previous lecture. Well, if you can remember, we discussed about the sampling distribution, which is a theoretical probability distribution of a given statistic, right? That you get from all possible random samples of a given population. The important thing is, as you can well imagine, it's a tedious job to draw sampling distributions for each and every sample or variable under consideration. But we don't have to worry about it. As statisticians have already developed sampling distributions for all common statistics. So what the researchers like us have to do is we have to just draw a sample from the population and then we can either manually calculate the test statistics, or we can use the computer statistical software to analyze the data. There are so many computer statistical software programs which we can use. Next, we discussed about the construction of a confidence interval. And if you can remember, we discussed that in real life, it's not possible to know the true population values unless you can do a complete census. So we discussed about the necessity to know a range of values in which we can say that with a certain level of confidence that our population value would lie. "95% confidence interval equals mean plus or minus 1.96 into standard error." And it's important to know the 99% confidence interval and 90% confidence interval too. 99% confidence interval is mean plus or minus 2.58 into standard error, whereas 90% confidence interval equals mean plus or minus 1.65 into standard error. Then reference range for any given biological parameter equals mean plus or minus 1.96 into standard deviation. Having said all that, let's move to the lecture proper. The outline. First, we'll discuss the parametric tests versus non-parametric tests. Then one-tail test versus two-tail test. The Z test, the Z distribution. Then one sample hypothesis testing for Z using the Z test. Then comparing two means using the Z test. The T distribution, independent T test, one sample T test. Then two sample independent T test. Then the paired T test. That is the outline for the current lecture. So by the end of this lecture, the student should be able to identify parametric tests and non-parametric tests, Understand the difference between one-tailed test versus two-tailed test. Describe the standard normal distribution. Apply the one-sample Z-test for hypothesis testing. Apply two-sample Z-test for hypothesis testing. Sixth one is compare and contrast the T distribution with the Z distribution. Apply the one sample t-test for hypothesis testing. Apply the independent two sample t-test for hypothesis testing. And finally, apply the paired t-test for hypothesis testing. So the statistical tests are broadly divided into two groups, the parametric tests and the non-parametric tests. The parametric tests actually use an underlying population for assumptions. And the examples are the Z-test and the t-test, which we hope to cover in this lecture. The non-parametric tests do not use an underlying population for assumptions. So therefore, it is also known as distribution-free tests. An example is the chi-square test. A little bit more about the parametric tests. They are used for quantitative variables in the continuous form and the data measured in interval or ratio scales and when the data follows a normal distribution. A one-tailed test would be used when the study has to test whether the population parameter being tested is either lower than or higher than some hypothesized value. So based on the alternative hypothesis set for a study, a one-sided test can be either left-sided or right-sided, right? So then what is a two-tailed test? A two-tailed test is a method in which the critical area of a distribution is two-sided and tests whether sample is greater or lesser than a range of values. So here we test for a difference. So we have not stated whether it's greater or lesser, but we say there is a difference exists or a difference does not exist. So that is how we write the null hypothesis and the alternative hypothesis. So these are the critical values that we get from the respective statistical test tables. So where the Z test is concerned, it's very easy if you know these values by heart. These are the critical values for the given alpha levels. These are the commonly used alpha levels. These are commonly used alpha levels. So if you can by heart these values, you don't actually have to use a Z table for hypothesis testing. Moving on to the Z test. Z test is a statistical test used to determine whether two population means are different when the variances are known. So therefore, it is a hypothesis test. Some key factors you should know. First one is a statistic follows a normal distribution. Second one, Z statistic is the calculated Z score. The third one is Z score equals the number of SDs around the mean. Fourth one you should know is Z test is performed when sample size is large. particularly when the sample size is more equal to 30. Then it is performed when the variance is known. We discussed about the standard normal distribution in the last lecture. However, just to reiterate, the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. Moving on to the one sample Z test. It is a test used to determine whether a particular population parameter, which is mostly the mean, significantly differs from an assumed value. So as the definition goes, it estimates the relationship between the mean of the sample and the assumed mean. The standard normal distribution is used to calculate the critical value of the test. So, like in all other parametric tests, this test also assumes that the data are from a random sample collected from a normally distributed population. So, let's see how we can calculate the Z statistic. For any given statistical test, the common equation is test value equals observed value minus expected value divided by the standard error. So when it comes to the Z statistic, then Z equals the observed value is the sample mean minus the expected value is the population mean, which is represented by mu, divided by the standard error. We learned how to calculate the standard error last week, so you know how to calculate it. So when you don't have the population standard deviation, you can use the sample standard deviation instead. So the key to these symbols are given here. So let me show you the steps you need to follow in doing a hypothesis testing. A simpler format that you need to stick to when you are doing examples or when you are doing your sums for your exams. Please follow this format. The first step is to state the null hypothesis and the alternative hypothesis. Then secondly, find the critical values. You can do this by referring to the respective tables, statistic tables. Then with regard to the Z, Z test, you need to by heart a certain common table values for the given common alpha levels. Particularly now say 0.05 alpha level. One tail value and the two tail table values you need to know. So the third one is compute the test value that you can do by applying whatever the given data to the formula. Then compare the calculated value with the critical value and make a decision whether you should reject the null hypothesis or whether you should not reject the null hypothesis. Then finally, you need to summarize the results so that the reader or the examiner can understand whether you can interpret these results or not. So let's look at an example where we can use the one sample Z test for hypothesis testing. So a sample of 400 male medical students has a mean height of 67.47 inches. Is it reasonable to regard the sample as a sample from a large population with a mean height of 67.39 inches and a standard deviation of 1.3 inches at a 5% level of significance. So the first step is to state the null hypothesis and the alternative hypothesis. So the null hypothesis is mu0 equals mu, that is 67.39 inches. So the alternative hypothesis is that mu0 does not equal 67.39. And these are the statistics that we are going to use for the computation. The next step is to find the critical values. So it would be easy if we have a diagram of the null hypothesis distribution. So here we are. So this is the standard normal distribution for the null hypothesis under consideration. So since this is an hypothesis is tested for no difference, it is a two-tailed test. So the area under the curve at each tail end would be 0.025, right? Then, so the next step is to compute the test value. We'll use the equation, the formula you just learned. So the Z equals x bar minus mu divided by the standard error. So the answer is 1.231. So let's see whether we can reject or accept the null hypothesis. So the fourth step is to compare the calculated value with critical value and make a decision. Let's look at the diagram once again. So the calculated value here is 1.231 falls to the left of the critical value, that is 1.96. So we can only reject whatever is in this region and this region. So this value being a plus value 1.231 falls somewhere here. So therefore, can we reject it? Can we reject the null hypothesis? We can't, right? So the calculated value, irrespective of whether it's a plus value or a minus value, is less than 1.96. So therefore, we can write the decision, the final conclusion, and make a summary like this. The calculated value of Z, which is 1.231, is not in the rejection region, right? That is the critical region, here and here. Therefore, we cannot reject the null hypothesis. And we can ultimately conclude that this sample, as a sample from a large population with a mean height of 67.39 inches and a standard deviation of 1.3 inches at a 5% level of significance. So let's look at the two sample Z test now. So the two sample Z test is used to compare the two means of two samples to see if it is feasible that they come from the same population. So the requirements for this test are two normally distributed but independent populations. Rho is known, that is the variance. The variance should be known, and the samples must be greater than or equal to 30 as for one sample is a test. Then the null hypothesis is the population means are equal. in practice, the two-sample z-test is not used often because the two population standard deviations, row 1 and row 2, are usually unknown. Instead, sample standard deviations and the t-distribution are used. Let's look at the formula for the z-test comparing two means. So if you can remember, any given test statistic equals the observed value minus the expected value divided by the standard error. So in this case, there are two samples, so we are looking at the difference. So this is the observed difference between the samples. Then this is the expected difference and divided by the standard error. So if population standard deviations are not known, we can use this equation and substitute the sample standard deviations in place of the population standard deviations. Let's look at an example to understand hypothesis testing using two-sample z-test. Let's say the amount of a certain trace element in blood is known to vary with a standard deviation of 14.1 parts per million for male blood donors and 9.5 parts per million for female donors. Random samples of 75 male and 50 female donors yield concentration means of 28 and 33 parts per million respectively. What is the likelihood that the population means of concentrations of the element are the same for men and women? So the first step is to state the null hypothesis and the alternative hypothesis. Since we are looking at the difference between men and women, we can state the null hypothesis as mu1 equals mu2, or we can state it as a difference mu1 minus mu2 equals 0. That means no difference. Alternative hypothesis as mu1 minus mu2 does not equal 0. So the next step is to find the critical values. Let's look at the null hypothesis distribution. So since this is a testing of no difference, we can use the two-tailed test, and if we take the alpha level as 0.05, because this is a biological test, we can see that the critical values would be 1.96 at each end, at each tail end. The area beyond this critical value at each end would be 0.025. Actually, these things you can by heart. The Z values, the Z table values, and the Z critical values for each alpha level given, each common alpha level given. The next step is to compute the test value using the equation we learned. So to calculate the Z value, we need to subtract the expected value, expected difference between means by the observed difference of means and divide by the standard error. So let's see now what is the expected difference between means according to the null hypothesis, it's 0. Therefore, we can compute the Z statistic like this, and the result is minus 2.37. So the next step would be to compare the calculated value with critical value and make a decision. Let's look at the null hypothesis graph again. And as you can see, the calculated value falls within the critical region, and we can conclude that the calculated value is in the rejection region, since 1.996 is smaller than the calculated Z statistic. Then we can conclude that the sample means are different at a 5% significance level. Let's look at the t distribution. It's a family of curves, and for each degree of freedom we can draw a separate curve. This curve is flatter than the standard normal distribution and have a thick tail end. More flatter and these curves have thick tail ends. So when the sample size increases, the curve looks more like a standard normal distribution. And these curves are also bell-shaped and are similar to the standard normal distribution. They are unimodal, just like the Z distribution, and the mean, median and mode falls in the center, dividing the each curve to two symmetrical halves. And the variance, of course, is different. It's more than 1. T-test, or the student's t-test, is a method of testing hypotheses about the mean of a sample, a small sample actually, drawn from a normally distributed population when the population standard deviation is unknown. So it was William Seeley Gossett, an Englishman, who actually developed this test. So let's see what are the differences between Z-test and the t-test. When comparing and contrasting the Z-test with the t-test, where applications are concerned, Z-test is used when population variance is known, whereas t-test can be used when population variance is not known. Z-test is used for larger sample sizes, particularly for samples more than or equal to 30, and t-test can be used for smaller sample sizes like less than 30. So what are the assumptions? Both tests assume that there's an underlying normal distribution, but the Z-test also assumes that all key points are independent, whereas the t-test does not assume all points are independent at all times. The convenience. This is very important because the Z-test, as you know, is more convenient as it has the same critical value for different sample sizes. That is why I said at the beginning of the lecture that you can even by heart certain critical values corresponding to commonly used alpha levels. However, the t-test is less convenient in that regard, as separate critical values exist for different sample sizes. Independent one-sample t-test. So, the one-sample t-test compares the mean score of a sample to a known value, usually the population mean. The basic idea of this test is a comparison of the average of the sample, that is the observed average, and the population, which is the expected average. So with an adjustment for the number of cases, because the sample size is small, the test makes some adjustments for the sample size and the standard deviation. Therefore, this is one of the most popular small sample tests, widely used in all disciplines including medicine. Formula for the one sample t-test. So again, the common equation is the test value equals observed value minus expected value divided by the standard error. So it's very much like the Z test. So it's the sample statistic minus expected population mean and divided it by the standard error. This is the t-table, and you can find the table values using the degrees of freedom and the given significance level. Let's look at an example for hypothesis testing using one sample t-test. A physician claims that joggers' maximal oxygen consumption, denoted by VO2 max, is greater than the average of all adults. A sample of 15 joggers has a mean of 43.6 milliliters per kilogram and a standard deviation of 6 milliliters per kilogram. If the average of all adults is 36.7 milliliters per kilogram, test the hypothesis claim at alpha equals 0.01. So the first step is to state the null hypothesis and the alternative hypothesis. For that, we have to focus on this statement that VO2 max is greater than the average adult. So, therefore, the null hypothesis would be the population mean is less than or equal to the average of the normal population, that is 36.7. And the alternative hypothesis would be the claim, that is mu is more than 36.7. So the next step is to find the critical values. For that, we need the null distribution. So this time, because we are testing the statement that the VO2 max is greater than the average of all adults, it is a right-sided one-tailed test that we need to use. And the degrees of freedom is calculated by sample size minus 1. So in this case, since the sample is 15, the degrees of freedom will be 14. So the next step is to find the critical values, you need to refer to a t-table. So this is the null distribution, and the value from the t-table corresponding to alpha level of 0.01 and degrees of freedom 14 is 2.625. Let's look at the table. So the degrees of freedom is 14. Degrees of freedom is 14 and alpha level for one-tail test is 0.01 here. So 14 and come down from here 0.01 significance level, and our value here is 2.625. So we have marked it here. The critical value is plus 2.625. We don't have a negative value because this is a right-sided one-tailed test. So the next step is to compute the test value using the one sample t-test equation. So here the observed value or the sample mean is 43.6 and the expected value, that is the population mean, is 36.7. Standard error is 6 and sample size is 15. So the calculated T is 4.45. Next step is to compare the calculated value with critical value and make a decision. Let's look at the null distribution again. So our critical value is here to plus 2.625 and the calculated value will fall somewhere beyond the critical value in the critical region. So this is the critical region beyond the critical value. Therefore, we can summarize the results as reject the null hypothesis as the calculated t-value falls in the critical region. Therefore, we can conclude that jogger's maximal oxygen consumption is greater than the average of all adults at alpha equals 0.01. Moving on to the independent two-sample t-test. Any statistical test that uses two samples drawn independently of each other and using t-distribution can be called a two-sample t-test. So such a test is used to test whether population means are significantly different from each other using the means from randomly drawn samples. So we make certain assumptions. It's assumed that the values are independent of each other and random sampling has been used and data in each group are normally distributed. Data values are continuous and the variances of the two independent groups are equal. The formula for independent two-sample t-test. Let's start with the common equation. Test value equals observed value minus expected value divided by the standard error. So next we calculate the pooled standard deviation. To arrive at this equation, you need to find the pooled standard deviation because there are two standard deviations. We are going to pool it. The idea is that this estimate adjusts for different group sizes. So let's see. The square of the pooled standard deviation is given by this equation. The standard error is given by this equation. So that is the standard error of the difference between means is given by square root of pooled standard deviation, the square of the pooled standard deviation divided by n1 plus square of the pooled standard deviation divided by n2. So the final equation for the standard error of the differences between two means is this. It can be calculated by multiplying the pooled standard deviation by the square root of the 1 divided by sample size, first sample size, plus 1 divided by the second sample size. So the t statistic can be found by taking the difference between the sample means and dividing it by the standard error of the difference of sample means. Let's look at an example for hypothesis testing using independent two-sample t-test. An experiment was conducted to determine whether intensive tutoring, that is covering a great deal of material in a fixed amount of time, is more effective than paced tutoring, that is covering less material in the same amount of time. Two randomly chosen groups were tutored separately and then proficiency tests administered. Use the significance level of alpha equals 0.05 to test the hypothesis. The summary statistics are given in this table. As you can see, for the intensive group, the sample size is 12 and the mean for the proficiency test is 46.31 with a standard deviation of 6.44, and for the paced group, the sample size is 10 and the mean for the proficiency test is 42.79 with a standard deviation of 7.52. So the first step is to state the null hypothesis and the alternative hypothesis. Now, when you look at this question, the first statement says to determine whether intensive tutoring is more effective than paced tutoring. So therefore, the null hypothesis would be mu1 less or equals to mu2, and the alternative hypothesis would be the claim that is mu1 is more than mu2. So the next step is to find the critical values. So let's look at the null distribution, and as you can see, the critical value here is 1.725. How did we find that? We need to know the degrees of freedom and the alpha level. So this is a one-tailed test because we are seeing whether the means are not just that they are different from each other, but whether one is greater than the other. So which means it's a right-sided one-tailed test. So let's see how we can find this critical value using the t-table. So here is the t-table, and our degrees, the calculated degrees of freedom is 20, and the alpha level under consideration for the one-tailed test is 0.05. So degrees of freedom 20 and alpha level 0.05 for one-tailed test. So 20 and 0.05. So the value is 1.725. So take a look at how we have calculated the degrees of freedom So it is by adding the two sample sizes and deducting 2 out of it. So if you look at this column, 12 plus 10 is 22, and then you reduce 2 from it to get the degrees of freedom for the two sample t-test. So the next step is to compute the test value, and let's see. Now first, at the first step, you need to calculate the pooled standard deviation, and when you substitute these given statistics to the equation here, the square of the pooled standard deviation is 48.25, and when calculating the test statistic, you use the difference of sample means divided by pooled standard deviation into square root of 1 over n1 plus 1 over n2, and the squared pooled standard deviation was 48.258. So the pooled standard deviation is 6.95, and you substitute all these values to the equation, and the calculated test value is 1.1828. So the next step is to compare the calculated value with critical value and make a decision. So again, let's look at the distribution, the null distribution. And as you can see, the calculated value is less than the table value, that is the critical value. So therefore, this value does not belong to this critical region where we reject the null hypothesis. So we can conclude the computed t of 1.18 does not exceed the table value. So the null hypothesis cannot be rejected. This test has not provided statistically significant evidence that intensive tutoring is superior to paced tutoring. Moving on to the paired t-test. They are also known as dependent samples t-test, the paired difference t-test, the matched paired t-test, and the repeated samples t-test. So in general, what we mean by a paired t-test is the samples are paired or matched, and every observation in one sample is linked with an observation in the other sample. So in other words, the samples are dependent. So as we have stated here, a paired t-test is where you run a t-test on dependent samples. So dependent samples are essentially connected. So they are tests on the same person or thing. So some instances where we run the paired t-test, so the two tests on the same person before and after an intervention, then blood pressure measurements on the same person using different equipment. So same person is important. Then twin studies using twins, and sometimes the matched studies. So those are the instances where paired t-tests are used. The assumptions regarding a paired sample t-test. The variables are continuous, and the observations are independent. The dependent variable follows a normal distribution, and there are no outliers. So equation for paired t-test. Here this is the sum of the differences, and this is the sum of the square differences, and this is sum of the differences squared. So when we look at an example, this will be more clear to you. Example for hypothesis testing using paired t-test. Scores of a quiz before and after an intervention are given below. Find out whether there is a significant difference in the scores at alpha equals 0.05. So, in the table given here, for each subject, the before score and the after score is given and is kind of matched. Same row gives the before score and the after score. So the next step is to state the null hypothesis and the alternative hypothesis. So focus on the word difference. So the null hypothesis would be mu1 equals mu2, or that there is no difference. Mu1 minus mu2 equals 0. Then alternative hypothesis would be mu1 does not equal mu2, because here the word is difference, right? Then find the critical values. So for that we need the degree of freedom and the alpha level. So alpha level we already know it's 0.05, and the degree of freedom we can the degrees of freedom we can calculate by reducing 1 from the sample size. So the sample size is 11 here. So it's 11. So the degrees of freedom is 10. And as stated here in the question, we are looking at the difference in the scores. So it's not right side or left side. So we will use a two-tail test. So let's look at the null distribution. So the critical values taken from the table would be plus 2.228 and minus 2.228. So how did we arrive at these values? Let's look at the table. So the degrees of freedom is 10. So it should be here. And the significance level for two tails is 0.05. So 10 and 0.05, two tails. So it's here 2.228. Right. So moving on, the next step is to compute the test value. For that, we need to do some initial calculations. We can add another column and find out the difference between the two scores, the before score and the after score, and then square the differences. Then we add up the differences column and the squares of the differences. So then we apply these to the equation we use to calculate the test statistic. So we know the sum of the differences That is, sum of the differences here is minus 73. Sum of the differences is minus 73. And then sum of the square differences. So sum of the square differences, this is the one. So that is 1131. And then sum of the differences squared. So this is the sum of the differences. Minus 73. You square it. Then you get 5329. So we'll apply those to the equation. And then we get the test statistic as 2.74. The next step is to compare the calculated value with critical value and make a decision. So again we'll look at the diagram, the null distribution, and as you can see, the computed value is greater than the table value, right? So it falls in the critical region, right? The critical region is beyond this critical value. So the calculated value is larger than the table value. Therefore, we can conclude the calculated t-value lies in the critical region. Therefore, we can reject the null hypothesis and can conclude that the scores before and after test are statistically different at 5% significance level. Now we have come to the end of the lecture. In this lecture, we learned about 5 different types of statistical tests that can be used in different occasions. We learned about the one sample Z test. Then we learned about the two sample Z test, which can be used to compare two means. Then we learned 3 types of t-tests. If you can remember, we learned 2 types of independent tests, the one sample t-test and the two sample independent test. Then finally, we learned about the paired t-test. So I hope you have learned a lot through this lecture, and if you have any doubts, please don't hesitate to contact me, and please fill up the feedback form and do the quiz so that you would know where you stand. Thank you.